in Jeddah. He graduated with a master and PhD degree from the nuclear engineering and engineering physics at the University of Wisconsin in Madison, United States. In 2001, he started a position as an assistant professor, then as an assistant research scientist, and then as an associate research professor in Abdulaziz City for Science and Technology in Riyadh, where he worked in different fields at the institution, in the fields of space, energy, materials, and plasma science and technology. However, in 2021, he took an early retirement and started his own company, which he's going to talk about. It's called Gases Electronics, which is specializing in commercial research and development in neutral and engineering sciences. The floor is yours, Dr. Ahmed. And I really would like to ask all the participants to mute their a few seconds, and mute their microphones. Dr. Hussein Aina is on. Dr. Amr is Hussein Aina. Please mute your system. Okay, Dr. Ahmed, the floor is yours.
شكرا دكتور غسان. Thank you, Dr. Hassan, and everyone of the Arab Physical Society and guests. The talk today is about hybrid plasma source, HPS, which is an invention that was conceived almost 11 years ago. It wasn't at that time under my company, but it was when I was working as an assistant professor at King Abdulaziz City for Science and Technology in Riyadh. So what you see in this picture, you won't see it again in the presentation, but this is the pre-prototype of what we've done. So basically, for the people familiar with the laboratory for microwave, for example, this is the step 2 knowledge for microwave tube, and this is the early structure of the tube that we did the hybrid plasma source. Here, the difference is the permanent magnets that you can see everywhere. So this just is a sketch of the real machine that we're gonna present, describe, and analyze in terms of data later on. So this is trying. Okay. Before we go on, I promised Dr. Shaban that I'm gonna put this presentation about the next upcoming second Arab Physical Society summer school, the second one on advanced physics. The venue will be in the City for Science and Technology in Cairo, in Egypt, by the end of August 2024. So we encourage students, professors, master level students to attend the second school, and more information you can find here at the link for the Arab Physical Society. So, introduction. What is physical plasma? Here, I know that other people in under the for the lectures of the Arab Physical Society spoke about plasma for me, including a good dear friend of mine, Dr. Ali Abdu. There is so many ways you can define plasma depending on the context. Whether it's industrial, whether you're pursuing fusion, whether you're pursuing semiconductor fabrication. So you have to know the problem, and then you have to know afterwards how you conceptualize the plasma you're dealing with. I'm just going to simplify it here very simply. You have neutral gas and you have plasma, and they're together in a chamber. That's what it is. The plasma is basically energized. People tell you will give more heat. I prefer the word energized gas. So energized gas will give you plasma, physical plasma. And then you have the neutral gas sitting there, and they are coexisting in the vacuum chamber. This is the conception for industrial plasmas. This is what people need to know. You're ionizing a gas further. It is slightly ionized, okay? You do this usually with electric field breakdown. The reason why we pursued this invention was at the time, and still this is the requirement for the semiconductor industry, they wanted the highest plasma density that they can get at the lowest, reasonably lowest pressure, and also with the lower electron temperature, so as not to damage the substrate that they are dealing. That was the challenge then, still it is now. Why? Because plasma tools, for many industrial reasons, has little to do with physics, basically. They still suffer from unstable working conditions. And there are many examples to talk about. For example, now we're going to talk about electron cyclotron resonance. Hello, can you hear me?
Yes, we can hear you.
Yes, we can hear you.
Thank you. So, unstable working conditions, actually. So, a new type of hybrid electric discharge. I was talking about the ECR, electron cyclotron resonance plasma source. For example, Hitachi, as a company, came up with a nice tool at low pressure, delivered all the requirements, seemingly all the requirements, ultra low pressure, and it delivered a stable condition, working condition with high density. But the industry did not adopt it because there are other bigger players. So now it has only one segment of the market. So this is how these things work in terms of plasma semiconductor fabrication towards market. So what we have done here? We have grabbed, well, now we have people who studied early versions of the plasma sources. They know what is an inductively coupled plasma source? What is a capacitively coupled plasma source? These are the early versions of the radio frequency, RF. They also know the thermionic emission plasma source that we use in the laboratories for fundamental plasma experiments. Now, later, all these years passed by, since the late 70s, early 80s, what we're left out with is either radio frequency or microwave-based sources. Microwave at a certain gigahertz frequency, RF at a certain megahertz frequencies. They are well understood and they are delivering. So we selected the best of two. The best of the microwave is the electron cyclotron, the ECR. The best of the RF is the helical, the so-called helical. Now, this is just to explain to you qualitatively what is ECR, what is helical plasma. The ECR uses electron cyclotron resonance. Everybody knows here what is electron cyclotron resonance to ionize the plasma. You are injecting microwaves, and there are free electrons there. Okay, and there is synchronization that happens, and some sort of electric field that is involved. This text, very simple, tells you when this resonance happens, and it's nice and it's optimum for delivering the energy to the gas and getting a nice high density plasma at low pressure. That's good. So that's one at hand we have. Second one that was invented, it's called helical discharge. It's the same as the RF, the ISP, except for the component of the magnetic field, which is directed along the axis of the antenna of the RF. Here also you get a nice ionization efficiency with a greater typical ISP, or inductively coupled plasma. So this is what we've done. We grabbed the two of them and we said, just let's combine it together. Each one of them in a different frequency range. ECR in the gigahertz microwave, 2.45, and the other is in the 13.56 megahertz. Different frequencies. This is a sketch of the apparatus. We're going to see the real machine soon. You see a tube here, which is a quartz glass. Let me just use this text here. Discharge chamber. It is 4.8 centimeter diameter, 70 centimeter in length. This chamber was kept under a very low base pressure. You're talking about, 6, 7 to the 7th milliton, to minus 7 milliton. 6, 7 to the minus 7 torr. Okay, so which is very low base pressure, and argon was used as a feed gas. The Helicon RF, we used a 10 centimeter long Nagoya Type 3 RF antenna. It looks like this. This is the antenna here. I want to just look at the sketch. This is the antenna. It's not H. It is around the cylinder, but that's the shape of the Nagoya Type 3 antenna that we use for Helicon. This is the ROI, region of interest. This is our region of interest because we have the magnets are here and the direction of the magnetic field, okay, that we use. This is the microwave source coming from here. This is the antenna for the RF, and these are the magnets, okay? So this is the ROI, this is the region of interest where we produce the high density, we call it sometimes ultra high density. Okay, and then the antenna was driven again by 15.56 megahertz RF power supply of power up to 3 kilowatts. Electron cyclotron resistance, spoke about that, 2.45 gigahertz. Oops. Magnetron source circulator and stub tuner. I showed that in the image at the beginning. 2000. This is not right. It's 2 kilowatt actually, not 2000. 2000 watts, not 2000 kilowatt. So this will be changed. 2 DC driven variable magnetic field coils. Also, I will show these now soon. Were placed at each end of the antenna to produce an axial magnetic field of up to 0.1 Tesla, 1,000 Gauss, up to 0.1 Tesla. Okay. We can talk about technical problems actually with these things later. I would like some of the questions actually be directed into the technical and engineering challenges as much as we talk about the physics. The 2 coils were 10 centimeters in diameter, 4 centimeters spacing between them. Actually, they won't survive more than 5 or 6 minutes. This is an engineering problem. But then we were doing a proof of concept. So 5 or 6 minutes, and then they were heating up beyond the ability to continue the discharge. Diagnostics. We're happy that we're able to implement OES, optical emission spectroscopy. We were successful in doing that. We picked a suitable collision and radiative model. We did the fitting for the line intensity. That looked nice. We used the line intensities. We have an escape factor for people who are not familiar with the optical emission spectroscopy. The escape factor is basically the line of sight radiance associated with the line of sight radiance of the radiation. This is A, which is the emission Einstein coefficient, not the absorption one, and this excited state density. You will find all the valence equations and coefficients in the reference that we published, basically, that I put at the end of this talk. And then the calculated CR model ratios are found by the reference ratios compared to the measured line intensities nicely, and the electron temperature and plasma density values were found. These are the emission lines. They look nicely. This is the collisional radiative model. This is the OES measurements. And so this is how we get the data. Before I get to the data, I will show the operation of the machine. This is the machine when it's operational. These are the magnetic coils that I described, okay? And they are not permanent. They are variable, okay? This is assembly of the microwave. So we deposit microwave from here. Inside here, this is the inside basically. This inside this thing here this is the inside. This very thing here inside here, this is the antenna that's delivering the helicon. So we will go back to this slide because once we discuss the data, we'll have to go back to this slide so that we can link things together. One feature very important here is the signature of ultra ionized argon, which is the blue shift of the color, which is indicative of the argon after which problems happen, such as, not problems, as issues start to come up, such as neutral depletion, and we'll talk about neutral depletion a little bit. Anybody who looks at this thing going to the vacuum will see how open in terms of how not regulate the mass flow, the whole discharge. It's leaking to vacuum, okay, and we can't claim that it's actually finite. Even the flow rate is regulated. That's what it is. Pumping, gas from here, you ionize it, and it's straight going to the pump. We don't know what's happening all the way here in terms of pressure and all these things. This is the power supplies down here for the RF and for the CCR, for the Helicon, for this. These are data. What do we care about in all of this invention? We care about the electron temperature and the plasma density.
You're back.
Let's see. We can resume recording if you want.
It is still recording, Dr. Ahmed.
Okay. Let's see. If you allow me. I'm getting full screen. I don't know. I can share probably now. Share screen.
Yeah.
But if I share screen, it's going to be.
Yeah, we are. That's good. It's good. We're on.
Are we?
Yes.
Okay.
Yeah.
All right. Let's see. Okay, I'm trying to find something, and then. All right. So we're back. So this is the pictures of the discharge. We're going back to, inshallah, after the presentation of the data, and we will describe many of the features. I just want you to remember this blue shift right in the middle here. Okay, it means a lot of things, and we'll get back to it. Now, experimental results. What do we care about? We care about electron temperature and plasma density, or what we call electron density. Okay, electron temperature, you can see that it scales with the pressure from 0.1. This is the pressure range we chose. I think I will conclude that this pressure range is suitable. For example, when I spoke about the ECR that Hitachi invented, they went from 0.1 Pascal and below, and they did ultra low pressure. I don't think you can sustain an ultra high density plasma when you go that low. Okay, many other problems happen at ultra low pressure. I think this is, if many successes that we have in this invention was the choice of this pressure range, which is 1 millitorr to 10 millitorr. Even though we started from a base of 10 to minus 7 torr. Very clean, almost ultra low pressure, not ultra low, but almost there. 10 to minus 9 is ultra low pressure. We start from a base of 10 to minus 7, nice pumps, clean pumps, turbo pumps, and everything. And then we got this pressure, beautiful pressure range. Now, what's happening here? We have the electron temperature that is going down here. Now, somebody will say, well, listen, from 7 EV to 4 EV, this is a 3 EV differential. So, I mean, and then from 8.5 to 4.5, this is 4.5. Okay, this is another nice differential. But also, I like the feature of the drop. The delta T is always oftentimes in physics and thermodynamics. Delta T, and even in heat transfer, delta T is as important as T itself, or even the heat capacitance. That differential is important. How far you go from point A to point B in temperature. This is very important. In addition to the importance of the heat capacity and the heat transfer and the thermodynamics of the problem. So this is the combo, the combination, ECR plus Helicon performance for 3 points. This weren't easy to take by optical emission spectroscopy, by the way. But like I said, we're happy and successful that we took a nice OS data that show how the diagnostics were. The power. So I came here and I said, well, ECR, we chose a 500 watt. and we stopped there. And we selected midpoint range, which is 5 millitorr. We started 1 millitorr to 10 millitorr. We selected 5 millitorr, right down the middle. And we fixed the ECR, electron cyclotron, and we start varying the helicon, because we'll see in the conclusion the difference between applied power and applied power and deposited power. There's so many school of thoughts in this. And so what happens here is that you're scaling up and then you're saturating, and I'm going to talk a little bit about that. But at least there is an effect that as you go up with the power, you scale up in temperature, and that's supposedly not a good effect. That's not desirable, okay? Because you don't want the temperature, to go high with you, because you want to increase the density of the plasma, keep the electron temperature low, okay, at lower pressure regime. So what's happening in the density world? In the density world, they're scaling ECR again, being a nice source by itself, is performing in terms of increasing the pressure and the density. ECR is really nice source, okay? So it's going up, okay? And then here, with power, the helicon power wasn't doing much, and this will come back to this thing. The next slide of data will explain why things are like that. When you fix the pressure and you start increasing the power, the question comes up: what are you doing? Is it efficient expenditure of energy to get what you want? This question and many other questions is answered by this issue, which is called neutral depletion issue. Many people who start working in the business of constructing very high density plasma, they will inevitably run into this issue, which is called neutral depletion. From the middle of the discharge, basically, I want you to imagine with me this. Inside the plasma chamber, you have plasma inside. The plasma, like I said, in the middle, the plasma, and then the neutral gas. You're ionizing the neutral gas to produce plasma. Low temperature plasma usually is 10% ionized, and the rest is just neutrals. But this neutral behavior is very important. Some researchers found that even 1% change in the plasma density affects the whole body of the neutrals inside the plasma. And this has to do with a lot of issues, such as the steady state of the discharge. It has to do with the stable conditions of the discharge. So every time, if you go down here, you come across regime couplings of ionization and transport, ionization and recombination. Okay, you are depositing power, and you don't know you're doing which where. The key to understanding this is the pressure. Sometimes, are you doing it at low pressure? Are you doing it in high pressure? Is the plasma collisional? Is the plasma collisionless? And in the plasma world, we have definition, how we define what is a collisional, what is a collisionless plasma. Do we have coupling or not coupling of these issues? So we went one further step, and we have the data in our hands of the temperature and the density, the electron temperature and plasma density, and we said, well, this is in the literature, okay? A measure of depletion, neutral depletion or just depletion. So this nice formula, and we start calculating things. So if you look how the depletion degree is scaling with the pressure, again, the same pressure range, it's the same data, okay? We just plugged it in here, and you see the depletion degree. When the depletion degree goes down, this means that you're okay. You're okay. Your density is going up, your depletion is going down. It's logical, okay? So you see, from that point, we're okay. From that point of view, our discharge is doing fine. The depletion is going down because we just plugged in data of a density that's going up. It balanced out with the temperature. That's what came out. So even the increase in temperature wasn't. Increase in temperature was good in the big scheme of things in terms of the depletion. But that's an interesting curve here. We fixed at 5 millitorr, and we wanted to look at the depletion degree, and we start putting more helicon power. Okay. saturation, not saturation, steady, not moving. The depletion is not increasing and staying at 0.5. Ideally, the depletion right down the middle of the discharge gets to 0.1, even 0.1, even to 1. And at the walls, it gets to 0, okay? Because recombination takes hold of things. We found in our region of interest, let's go back to the region of interest, we found here, this is the region of, this is where all the magic is happening, okay, here. This is where the depletion is happening, this is where ultra-high density is happening, but what is the meaning of depletion being constant at one pressure that we picked, which is 5 millitorr, staying the same? It means the more power you're putting, the more helical power you're putting, you're not getting a behavioral change of the discharge, okay? And we're not the first people to point that out. Some people, some researchers, basically they looked at that issue and they said it's counterintuitive, okay? But that's okay. If you go back and you do further analysis, okay, into these coupling issues, you will understand why you put more power, you're not getting higher density, you balance temperature, looking at temperature and density, and in the end, the more power with nothing changes in the density, less efficiency. If what we've done was for the sake of the semiconductor tool manufacturing, that was the frame of work. But in reality, people care about that a lot when they design the thrusters, space thrusters. This becomes an issue. This becomes a big issue. And then the system is not closed, the system is open. And the issue of putting energy and efficiency that you're getting out of it, so that people went further and they looked at the power applied versus deposited. Where is it deposited, this power? And then they looked at different species. We looked only at argon, and so on and so forth. But the neutral depletion issue is the central issue in terms of, building high electron density power sources, whether for space thrusters. We say space thrusters because thrusters on Earth are not feasible. Space thrusters, or directly for semiconductor tools manufacturing. So in conclusion, hybrid ECR, helical plasma source, was constructed to demonstrate high plasma density at low pressure, applicability in industrial plasma tools. OAS plasma diagnostic technique was successfully used to measure the electron temperature and plasma density of the electric discharge. These preliminary data that we presented here indicate that the hybrid source reached the high plasma densities as scaled with high pressure. The electron temperature scaled faster in declining as the pressure increased. Highlighting the neutral depletion at fixed pressure, it was held steady. The plasma density values appears to decline with more helicon power applied. Possibly possible decoupling of ionization transport, ionization, recombination regime changes depending on discharge pressure, applied versus deposited energies, confinement, among other things. All these issues are important, okay? The selected pressure range seems suitable for a diverse range of experiment. The selected pressure range, we really truly believe that, the selected pressure range seems suitable for a diverse range of experiments in this novel approach. The reference, all that stuff that I spoke about is actually published, and this is a patent, US patent on the machine. And I welcome any of your questions. And for communicating, this is my email, my phone number in Riyadh. This is my company. We do so many of these projects here in Riyadh, mostly plasma physics. Thank you very much.